Hi there. We are doing Intro to Bio lecture video number 2. This section is about graphing, how to do or make a correct graph in this case. A graph. Graphs need 7 things to be done correctly. All right, here they are. We need to know what the graph is telling us, our title. We need to know what the information on the graph is. Would be labels, units. For example, this is showing you the label would be time, and the units we'd want to know, well, what is time passing? In this case, in seconds. We want to have scaling on the x and the y axis. You got to keep your scaling equal. What that means between 2 points, in this case, it always has to be 2, 2, 4, 6, 8, 10, 12. Or you can go by 500s, 500, 1,000. This will make more sense in the example I give you in a second. A scientific graph, ideally, if it is a number graph where you have points you're plotting, ideal graphs for science are number graphs, and we would create what's called best fit lines or best fit curves of our data. So these are only used for line graphs, and they're important to be done this way. And I'll explain that to you in a second also. We have the dependent variable and the independent variable. Well, we just had a section on the experimental design. Well, you may have remembered that the thing you're measuring in your experiment, your data, is your dependent variable, and that data that you measure would go on your y-axis as a result of your experiment. The information on your x-axis of your graph is what's called your independent variable. This is what you're testing. The thing that you're testing generally would go on your x. The results of that, what you're testing, the dependent, would go on your y. Using 70% just means stretch it out, make the graph big so you can utilize it to interpret it and to use it for estimations. And that'll make more sense in a second. Now here's a graph. What's wrong with this graph? Well, there's a bunch of things wrong with this graph. First off, I showed you the data table. In this data table, you may notice that these numbers, 14, 15, 19, 20, they're just put right there, right on the bottom of this graph. Then over here, 57, 61, 64, 60, those are right there. Well, first off, let me explain to you why the scaling is wrong. 57 to 61, that's 2. And then from 61 to 64, that's 3. 64 to 68, that's 4. There's 4, 3. The scaling is not equal. So this interval or the scaling is not good. This doesn't work. Over here, by 1, by 4, by 1, by 2, by 2. Not equal intervals or not equal scaling. When you make a graph like this, when you take your data table and your data table becomes your x and the information in your data table becomes your y, you'll put points on your graph and they will make a perfect straight line every time if this is how you make your graph. Okay, this is not a correct scientific graph. Let me show you what it looks like when it's done correctly. All right, this is a correct scientific graph. So here's the same data, all right? Here's the same graph but done correctly. 55 to 57 is 2, 57 to 59 is 2, 59 by 2, by 2, by 2, by 2, by 2. So the scaling in the interval is correct, all right? Next one, over here, by 1, by 1, by 1. Every one of these goes by 1. The scaling in the interval is correct here. Just so you know, on a scientific graph, you do not have to start at 0. In a mathematic graph, you generally will start at 0, but this is a scientific graph. You do not have to start at 0, all right? So then they plot the points. So the first one is 14 over 57 up. That's right there. Next one is 15 over 61 up, 19 over 64 up, and so on and so forth for all these points. All the points were plotted. Well, they're showing an upward trend, all right? But they do not form a perfect straight line. So in a scientific graph, you make what's called a best fit line. This is the line that is the best fit of your data. So it is an average of your data points. This is a best fit straight line, okay? If your data went up and then came down, you would have a best fit curve, but that is not the data that we have. This data is continually going up. So this is a best fit straight line, all right? It's an average of your data points. When you do this, you're able to do these two things called interpolate and extrapolate. And I'll explain that to you on the next page. So interpolate means Estimate. Give me an estimation of what would happen between two of your data points. So for example, here, 17 is right there. That's between data point 15 and between data point 19. I don't have data for 17 degrees Celsius, but I want to know what would probably happen if I did have data for 17 degrees Celsius. So you use your graph to do this. You start at 17, you go up to your best fit line because it's an average of your data, and it stops right there. Then, whoops, go back. So you go right there, then you come over, and you get there. So the answer here, interpolate, at 17 degrees Celsius, I would expect about 63 protozoans. That would be the answer. So we made an estimation between our data points, or we interpolated this information. 25 is over here. Well, why is this called extrapolate, not interpolate? Because it's outside of our data points. We don't have anything outside of here. So we stretch our line, and our line is now stretched out, so we can now have information outside of our data points, or extrapolate information. So we still here, 25, we go straight up, we end up there, okay? We come all the way over, and that puts us right there at about 74 protozoans is where we're at. So the answer for 25 degrees Celsius, we would get 74, and at 17, we would expect about, I believe it was 63. Now, on this graph also, your dependent variable, the number of protozoans, this is what's measured, that is on the y, okay? Your independent variable, the temperature in this case, this is what we're testing, it is on the x. I'm going to give you a way of remembering which one goes on which axis. The words are, there's two words you got to remember when you think of graphs. Dry, mix. Dry. The dependent variable is on the y-axis. The D and the Y help you remember that. The word dry. Mix. The independent and mix, the I, is on the x. So dry, the dependent is on the y. The independent is mix, is on the x. Okay? So in this case, temperature would be what you're testing, what you're measuring are number of protozoans. Finally, for this section, we got to learn a little bit about bar graphs. Well, bar graphs are generally used in science when you don't have numbers, for example, on your x-axis. So in this case, you're kind of gathering data and you're tallying data and you're putting it into a graphic format. Yeah, they're pretty, they're nice, they look good. We like the way they look. Most students would make a bar graph instead of a line graph if they could. The reason they do it is they like the way they look. They're more visual to them. But you cannot interpolate, you cannot extrapolate from this type of graph. You don't have a best fit average of your data. So this is why in science, if you can, you generally want to make a line, plot points, and make a best fit line so that you can extrapolate or interpolate from your information. Same thing here, okay? The x-axis, this is what's being tested. And in this case, they want to know the number of birthdays by students by month, the number of birthdays of students in a certain month. So here's the month, and here's the number of students that have birthdays in those months. The data doesn't necessarily go together. It doesn't form any certain pattern. So there's no interpolation. There's no extrapolation done from these types of graphs. Also, so this is the independent is on the x, dry, mix, independent x, and then the dependent, the number of students, depends on what month it is. Okay, that we will end our lecture there.